Hello, guys. We're going to talk more about fluids today. Getting to the meat and potatoes of the unit. So, I want to talk to you about the density unit. So first, let's review basically what density is. I think you should know this. So we're going to use the symbol for density of rho. So that's going to be, it's a Greek letter, and it's going to be density. So, and we're going to define density as mass divided by volume. That's a W. Let's try this again. Mass divided by volume. So it's going to have units of kilograms per meter cubed. So if you guys are familiar with doing density in chemistry, most of the time in chemistry, they will do units of grams per centimeter cubed, and that is not the same thing. So just be aware of that. So for example, common densities that you might want to know from physics is, in chemistry, it is water, right? I guess let's put it up here. Let's do water. The density in physics is 1,000 kilograms per meter cubed. And the density in chemistry is 1 gram per centimeter cubed. So those are very different numbers. It's the same number, but it looks very different. Okay. So what are we going to do with density? So a lot of the questions that you're going to see are going to be about comparing the relative and absolute densities of two objects. And there's going to be a lot of questions about buoyancy. So all of them are using buoyancy in some way to do this, to try and figure out the densities of liquids relative to each other. So we'll talk about how you find the buoyant force in a minute, but a very common method that they want you to use for comparing densities is basically saying, I've got this cup full of fresh water, and I have this cup full of salt water. How can I figure out which one's more dense? And the tools that you have are going to be a spring scale, which are just like a scale that you can hang a mass from and determine, the weight, right? Or not the weight exactly, but the net force pulling down on the spring. So you're going to have, I'm just going to draw it like this. Like a spring, and then, a hook or something, ball, whatever. And you're going to have a mass. And so you'll have a question like, how can I figure out which of these is more dense? And so what you're going to do is you're going to take your mass, you're going to attach it to your spring scale, and you can figure out the weight of your mass. And then when I put that mass into my fresh water, I guess let me draw another picture down here that has room for me to draw a free body diagram in it. I put that mass into the water, and it's attached to my spring scale. Beautiful. No one said you had to be an artist to be a physicist. And so what are the forces on this mass going to be? Well, as always, it's going to have weight. So I'm going to draw this in red. It's going to have its weight. It's going to have a tension going upwards associated with the spring scale. And it is going to have a buoyant force going upwards. I'm going to call it FB, or some people call it BF, some people just call it B, some people just call it F. So use whatever notation works. I think in your formula sheet, they actually just say F. But I'll have to check on that later. But FB is going to be buoyant force. Let's write that down. Okay. So those are the three forces you're going to have. And so the question is, when I draw the second container with salt water, will the spring scale read more or less, right? Because that's what we're going to be able to see and observe with our eyes. Those masses are exactly the same. Don't believe anyone tells you differently. Yeah. So what the forces here are going to be the exact same forces, just they're going to be scaled slightly differently, right? You're still going to have weight, and that's going to be the exact same weight because it's the same mass. You're going to have tension pulling upwards. There we go. Now you can see it. And you're going to have a buoyant force here. So if I want to compare the densities of the fluids, well, the density of the fluid is going to affect this buoyant force. We'll talk about how in just a second. So if I have, so this tension is the reading of the spring scale. Let me switch back to my black pen. Okay. This tension is the reading on the spring scale. So, and the weight is the exact same in both cases. So the difference here is going to be the buoyant force. So if I say I know the weight, I can measure it outside of the water, right? So I can say weight minus tension is equal to the buoyant force. And so the greater the buoyant force, the greater the density of the fluid. So we'll say buoyant force is proportional to density for now. All right, let's go to a new page. All right. So let's talk about that buoyant force equation. The equation for the buoyant force is going to be density of the fluid times the volume of the submerged portion of the object times acceleration due to gravity, which is, it's 9.8 meters per second squared. You should be familiar with that. So in the case, so because what we did before was we had a weight completely underwater. But what if we had a situation where you have your water up here, but your object is floating in it, right? Well, in this case, we know that the buoyant force has to equal its weight because it's not falling down, right? We know that, so let's write this down, buoyant force equals weight. And let's just write it as floating for good notation. So, yeah, so this part up here is weight is going affecting it, but the water that is the volume that I have to count, the volume submerged, is this part down here underneath the water, which is obvious to some of you, but it's important to remember. So I'm definitely taking the time to talk about it. So this part above is unsubmerged, which I'm going to call VU, because that's, I think, the notation AP uses. Yeah. So if we're looking for what is the buoyant force on this object, well, it's just equal to its weight, so it's just equal to mg. But if I wanted to figure out how much of it is submerged, right? What percentage of it is submerged, then I would could do some, a little bit more fancy math. So I could remember that density of the fluid, volume submerged, and G. So I'm just from now on, I'm just going to say this is VS. Okay. Sorry about that. I had a brief pause because I had some groceries delivered, because we're avoiding going to grocery stores and things and practicing good social distancing, as you guys should too. All right, so finishing. There we go. Times G. So what I'm saying is the buoyant force is equal to the density times the volume submerged times the acceleration due to gravity. Now, if I wanted to say which fluid has greater or lesser density and what percentages are those if I have two floating objects, well, in that case, I want to look at the volume, the ratios of the volume submerged. If it has more, because if we're putting the same weight in both of them, the weight will be the same, right? This will be unchanged. So what will change, though, is these two terms. This is also unchanged, right? Constant, let's just say. So these two terms are going to be what changes. So we're going to see something that would look maybe more like this. So you get your unsubmerged volume up here and your submerged volume down here, right? Or you might have another one that looks like okay, not to scale, but whatever. So then this one has less of its volume submerged and has more of its volume unsubmerged. So if it has less volume submerged, do you think it has a higher fluid density or a lesser fluid density? Because remember, I want rho V S, that's an S, should equal to M, because those guys are going to cancel. Right? So since this is a constant, if this term goes up, I should put this down here, Vs. If this term goes up, like it does here, then this term had to go down, right? So let's write that down. If, say hi to Cicero, Vs goes up, then rho density of the fluid has gone down. And of course, if volume submerged goes down, then density of the fluid goes up. All right, I think I'm gonna call it quits here for this video, and I'll see you in the next one, guys.